Alright everybody, please welcome back to our next chemistry video. Before we go any further, shout out to Alana for being so supportive of these videos and wanting more to be made, and thank you to all of you for how enthusiastic you have been for these. I'm sorry that there has been a big delay between video 2 and video 3, but now that the issues that led to that have been sorted out, there will be lots more videos in the next few weeks until we have finished our organic chemistry series, so be ready for that. Today we're going to be looking at some of the things that complicate the story of organic chemistry more than what we've seen so far. So far we've looked at alkanes, alkenes and alkynes and the simple shapes of them, but today we're going to get stuck into the very first of the things that make the story more complicated. And that comes down to this concept of isomerism, which we will get stuck into shortly. But firstly, I want to talk to you about branching chains. So if you look at this molecule here, you will recognize it as something that we've already seen. This is a simple skeletal formula with 1, 2, 3, 4, 5, 6, 7 carbons, which means it is a molecule of heptane. And there's not much else to it than that. But what if I was to do this and add on extra carbons branching off the main chain? This is called a branching chain. And we need to think about how we're going to deal with this sort of thing when we name our molecules. Now, if you look at this chain here, you might think we've still got this heptane chain down the bottom. So it's going to be a heptane molecule with this stuff coming off the side here, and we have to deal with that naming wise. But if you thought that, you would actually be wrong, because this bottom chain here is no longer the longest chain. The longest chain is now actually this one. And this is an 8 carbon chain. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So this is an 8 carbon chain, and so we're going to call this octane, because it is an octane chain. But then the question comes, what do I do with this section coming over here? I've got a carbon, and if you don't remember skeletal structures very well, this is actually a CH3 group. So what do I do with a CH3 group sticking off the side of my chain? Well, it turns out that we can just name this according to the same carbon prefixes that we've been looking at before. So if you remember that 1 is meth, 2 is eth, 3 is prop, all of that sort of stuff. This is a 1 carbon side chain, and because it's a 1 carbon side chain, we can call this a methyl group. And so we have a methyl octane. But which carbon is the methyl group sticking off? It is carbon number 3. So it is a 3 methyl octane molecule. Now these can get a little bit more complicated. As you can see in the case of this molecule here, we have the exact same backbone as before. We've got our octane backbone, but now instead of having simple octane and the 1 methyl group over here at carbon number 3, we now have a second methyl group here at carbon number 6. And so how are we going to name that? Well, again, it's a very simple starting point. We have the longest chain is the basis of the name, octane. And then we have methyl groups, so we're going to call it methyl octane. But we don't have just 1 methyl group anymore. We have 2 methyl groups, one at carbon number 3 and another at carbon number 6. So that's 3, 6 dash. And then we use the same prefixes that we use for things like double bonds, di, tri, etc. So we're going to call this dimethyl octane. So 3, 6 dash dimethyl octane. So that's branching chains. The key ideas are that it's possible for carbon chains to branch. Carbons can connect to each other anyway, and they don't have to just be in a straight line. But whenever we come across a branched chain, we always use the longest carbon chain as the basis for the naming of the molecule. That is the central part of the molecule's name, is the length of the carbon chain. And then we treat branches of the chain as more functional groups, like what we've looked at before. A CH3 group is a methyl functional group. CH2-CH3, which is simply a 2 carbon long chain, is an ethyl functional group. And then we have propyl, butyl, etc., but we're not really going to come across those as part of our syllabus. So the key ones to remember are methyl and ethyl functional groups, just like the name of the band who don't like letting me use their music. So have a quick look at this guy and see if you can figure out his name. Pause the video if you would need to. Alright, so the first thing we want to do here is find the longest carbon chain. You can see that there's a few different possibilities for this, but I'm just going to show you the most simple one. Let's start up here. Carbon 1, 2, 3, 4, 5, 6, 7, 8. So this is an octane chain again. And then if that is the longest carbon chain, that means everything else sticking off it is a functional group. So let's start off by writing the name here, octane. We then have a methyl group, another methyl group, another methyl group, and an ethyl group. And in this case, in the absence of any other interesting functional groups, what we're after is figuring out a way to number the carbons so that the lowest number of interesting things is coming off. So the sum of all the numbers of the things coming off the chain are their lowest value possible. So right now, if I was to proceed with the naming scheme that I have in front of me, I would have 3 ethyl, 4, 5, 7 trimethyl octane. But that is leading to some very high numbers. The alternative is I make this carbon over here carbon number 1, in which case I will have octane again. And then I will have 1, 2, 3, 4, 5, 6 ethyl, 2, 4, 5 trimethyl octane. Didn't quite fit all that in the one line. But you can see that if I've got the locants 2, 4, 5, and 6, 2 plus 4 plus 5 plus 6 is equal to 17, whereas 3 plus 7 plus 4 plus 5 up here is equal to 19. So this name here is to be preferred because that leads to the lowest overall sum of my locants. When you have a molecule like this that is fairly simple and there's nothing particularly fancy on it, like a double bond or a functional group like a carboxylic acid or something, then the numbering always happens so that the lowest total number of locants is given, which in this case is 6-ethyl 2,4,5 trimethyl octane. Now, another thing that can make the shapes of molecules more complicated is that molecules can also be cyclic. So a cyclic is where you have the exact same carbon chain, but instead of having a long open chain with 2 ends, you can have the molecule come back around and join onto itself. So this first molecule that I have in front of me here is cyclopentane. And you can see why it's called cyclopentane. It's called cyclopentane because it is 5 carbons, 1, 2, 3, 4, 5. So it's pentane, but it has made a cyclic. It has closed around onto itself and joined back at the start, and so we call it cyclopentane. Up here we have hexane, and so below where we have a cyclic version of it, that is cyclohexene, not cyclohexane. And up here we have a 1, 2, 3, 4, 5, 6, 7, 8. It's an octane, but it's not simply an octane, it's an octene, and not only that, it's an octadiene. So this is a 1, 4 dash octadiene, or the way that I prefer to name these things is octa dash 1, 4 dash diene. But then the cyclic version of it is a cyclooctadiene, which is a bit of a mouthful, but the best way to do this is to simply number our locants in a way that gets us to the lowest total numbers like before. So 1, 2, 3, 4, or 1, 2, 3, 4. It's exactly the same in both directions. So it is an cycloocta dash 1, 4 dash diene. And that is about as complicated as something like that will get. So the bottom line with molecules like this is that if you have a cyclic version of a molecule, you're going to have to make sure that you include the prefix cyclo in the name to account for the fact that it is a cyclic molecule. One type of cyclic molecule that is slightly more complicated is a molecule called benzene. Now it's important to notice that these things are not directly part of our syllabus, so you don't have to know too much about them, but they are very common and very important in organic chemistry, especially if you go on to study this at higher levels, so I do want to mention it to you quickly. Benzene, at first glance, looks like cyclohexane, but there is an important difference with the benzene molecule, and that is that it has 3 double bonds inside the molecule. So you can see there is a double bond here, and a double bond here. Now this double-headed arrow that I have here is what is called a resonance arrow. And resonance refers to situations where you can actually have double bonds moving into different places. So if you look at this molecule over here of benzene, you'll see that it looks almost exactly the same as this molecule over here, except that each double bond has moved one place over in the circle, leading to a new arrangement of double bonds. Now in benzene, what actually happens is you have all of your 6 carbons and 3 double bonds, and those double bonds can actually occupy either spot compared to where they are. So this double bond can just as easily be here, this double bond can just as easily be here, and this double bond can just as easily be here. And what that leads to then is a situation where you have a rapid transformation between both possible forms, and what actually forms is a mixture of both. And so sometimes we will draw benzene like this to show that the double bonds are actually spread out across the entire range of all their possible locations. And this leads to a situation where the electrons are actually spread out across the entire thing at the same time. This is called resonance, and it leads to electrons being able to exist across lots of different orbitals at once, which leads to interesting properties which we won't go into. But molecules like this, where you can have very long resonance forms of the molecule, are called aromatics. They were originally called aromatics because they had interesting smells, aromas, but the term has stuck, and so there are lots of different organic molecules now called aromatic molecules, and benzene, which is this molecule that we've looked at, C6H6, is the simplest version of that aromatic structure. Alright, so that leads us to this idea of isomerism. Now, an isomer is a situation where you have different molecules with the same molecular formula. This is a little bit counterintuitive because when we first learn about chemistry, we learn about simple things like we learn that H2O is water, or we learn that CO2 is carbon dioxide. So you think, right, I know the molecular formula, therefore I know what the chemical is. But in organic chemistry, the molecular formula is actually a very low resolution way of thinking about what a molecule is. It doesn't give us that much information. So this molecule that I've got down here would be 2-hexene or hex-2-ene, and that has the molecular formula C6H12. But I can't just look at that molecular formula C6H12 and think, right, I know that that is definitely this, because C6H12 could just as easily be a cyclic. Cyclohexane also has the molecular formula C6H12, or I could even have a 2-methyl grouped butane molecule. This is actually, if I go 1, 2, 3, 4, it is a 3,3 dimethyl but1-ene. Now the name of that molecule is not too important for this, but the key idea is that this molecule also has a molecular formula of C6H12. So it's possible for chemicals to have the exact same molecular formula, but a completely different structure. And that's where this word isomer comes from. Iso meaning same, mer meaning share, the same share of molecules, same share of atoms, but a completely different molecular structure. Now there are 3 different types of isomers. The simplest type of isomers are chain isomers, and that is where we take sections of our carbon chain and we branch them off into different places. So we've looked at this sort of thing already. So each of these molecules that I've just put up on the screen here have the exact same number of carbons, but they are just branched differently. Another type of functional group is a position isomer, and that's where you have a functional group moved to a different part of the molecule. So the example I have here is chlorine. If I have a chlorine attached to a carbon chain, each one of these different arrangements of the chlorine is a different isomer. And the last type of isomer that we can have is where we actually change the functional group based on where something moves to. So for example, if I have cyclopentane, that is different to pentene, even though they have the exact same chemical formula. So those are different functional groups. One is a cyclic, the other one is a double bond. Another example is where I could have an oxygen. If I have the oxygen on the end of the molecule, then I have an alcohol functional group. Whereas if I move the oxygen into the chain, I have an ether functional group. And we're going to learn a lot more about these different functional groups as we go. But the key idea is that there are three different ways we can form isomers. One is by changing the chain, another is by changing the position of a functional group, and the third is by changing the functional group in the way that we rearrange different things in a carbon chain. Now, the last thing I want to quickly talk to you about in this video is something that our syllabus asks us to be aware of, but this is actually simply revision of Module 1, and that is the idea of how the number of bonds around a particular atom affects its shape. So if you think about carbon to hydrogen bonds, like a simple methane molecule, for example, you have carbon, you have one hydrogen, second hydrogen, a third hydrogen, and a fourth hydrogen. What we can actually draw when we draw these sorts of things to show that this is arranged in a 3D way is we can draw a fat wedge coming out the front and a dotted line wedge going out the back. We then think about these two hydrogens as being in line with the page, this one going into the page and this one coming out of the page, and that makes a tetrahedral shape. So if you have a carbon that is making all single bonds, then the shape of the molecule around that carbon is tetrahedral, and that is right back to our Module 1 syllabus. If you don't remember that, go back and revise Module 1 to look at molecular shapes. If you have one double bond, that double bond behaves like a single bond in terms of our valence shell electron pair repulsion, or VESPA. And if it behaves like a single bond, that means that this double bond, this single bond, and this single bond are all trying to get as far away from each other as possible. And the way for them to do that is actually to be in the one plane with 120-degree angles in between each of them. And that makes a triangular planar shape, and triangular in molecular terms we call trigonal. So it's trigonal planar around any carbon with a double bond. And then finally, if we have a triple bond, that triple bond, for the sake of VESPA, acts like a single bond, and so this single bond and this triple bond are going to get as far away from each other as possible. The furthest away from each other you can get is a 180-degree angle. And so that is a linear molecule shape around that triple bonded carbon. So wherever you have all single bonds around a carbon, the shape of the molecule at that specific carbon is tetrahedral. Wherever you have a double bond, the shape of the molecule around that carbon is a trigonal planar shape. And where you have a triple bond, the molecule is linear. And remember, if you want to see any of these things for yourself in slightly more detail, I got these stills from the MolView website. I suggest you check out the MolView website and put in some of these different molecules and then just look at the 2D to 3D projections of them and have a look and see how they look in 3D, because it is hard to see what these things actually look like when you're only seeing 2D drawings of them. Remember that everything that happens in chemistry is in 3D, and 3D is the way that we should be thinking about what these things are actually like. 2D is simply for the sake of simplicity. So the key ideas for this video are that it is possible for different molecules to have isomeric shapes, which basically means that they have the same molecular formula, but a different chemical structure. There are different types of isomers. Remember, there are chain isomers, positional isomers, and functional isomers. There are actually other types of isomers as well that are too complicated for our syllabus, so we won't be going into them. Another key idea in this video is that chains can be branched or cyclic, and that is one way that we can change the way that atoms are arranged in the molecule. And the last key idea in this video is that if you have single bonds, you have a tetrahedral shape, double bonds are trigonal planar around that particular carbon where the double bond is, and triple bonds are linear around that particular carbon. So that is video number 3, all done and dusted. I will see you for video 4 on functional groups in the not too distant future. Oh, somebody help me. YouTube copyright claimed that methyl ethyl song, and now I've only got dodgy stock music to play at the